Welcome. This video is going to continue looking at solutions to the Section 2 questions from Chapter 1, starting with question 24. And question 24 asks you to find the empirical formulas of the following compounds. So you just have to see if you can divide all the subscripts by a common denominator, I guess. So this could simplify to CH if I divide by 2. B, I can also divide by 6 and get CH2O. Whereas C, there really is no common factor, I guess is what you call it. So this just remains C12, H22, O11. Doesn't seem very simple, but it's as simple as it gets. D, I can reduce this to C4, H9. And then E, pretty easy to reduce to C4, H7. F is the one, you might find it easiest to rewrite this C2, H4, O2, and then it becomes more obvious that this will reduce to CH2O. So why did they write it like this? Well, this is organic chemistry when they put it like this to show you that this is what we call a carboxylic acid. So it'll become clear why we write these formulas differently. But when you look at the empirical formula, like B and C are both sugars, and because their empirical formula isn't similar, it lets us know they're from different families of sugar, which is why some people can tolerate sucrose but not glucose, or some people can tolerate fructose but not sucrose. It's all about slightly different structures, going back to the empirical formulas. Question number 25, I've told a sample compound contains sodium, sulfur, and oxygen, and I've given these mass amounts for each and asked to determine the empirical formula. So your first step is you need to find your molar amounts of each. So if I divide by 23 grams here, sulfur, I'm going to divide by the 3207, and oxygen by the 16 to get my molar amounts. So here's the molar amounts I got for each. And what I like to do is I like to go ahead and write the formula with these ratios so I remind myself that's really what my subscripts are. It's just these ratios. And I see pretty quickly that Na and S have the same molar ratio, and it's smaller than the molar ratio for oxygen. So when I divide by my smallest molar ratio, Na is going to become 1, sulfur is going to become 1, but oxygen divided by 0.4256 is going to become 1.499 or 1.5. And so I don't quite have my whole number ratio, so I have to multiply the entire thing by 2 to get Na2S2O3. Number 26 appears like it's more difficult because now you've got water involved, but it's just a hydrate, so still fairly simple to do here. I'm going to go ahead and change my cobalt, change each of my amounts into their molar amounts. So I'm just going to pause here as I go ahead and get this step done. So now that I have my molar amounts, I'm going to go ahead and turn it into my equation, 0.3563. The sulfur is relatively the same, 0.03555. Oxygen, 0.1425. And then remember, since it's a hydrate, the water would be, actually the molar amount would be put in front of the water, the 0.2497 moles of water. So I'm still going to use the same process and divide by my smallest molar amount. And that includes the water. So now when I do this, my CO basically becomes 1, my sulfur becomes 1, my oxygen, when I divide by 0.03555, is going to round very close to 4, so copper sulfate, that makes sense. And then my 0.2497 divided by 0.03555 is going to be 7.02, or it's a hydrate with 7 water molecules in it. So number 27, you're told a street drug has the following composition. It's given to you in percents, but remember, percent is really just the same as a 100-gram sample. So I can convert each of these to molar amounts. So I've got the carbon set up, and that converts to 6.985 moles of carbon. Oxygen is going to be right around 10.248 moles of carbon. And then the nitrogen is going to be a little less than a half here, 14.01, 0.4111 moles of nitrogen. And the reason it's important is this is how law enforcement, et cetera, realizes when there's a new drug, a new street drug out there, is when the composition changes. And that's sometimes what makes it especially dangerous, because it may give the same effect to the user, but may have a very different effect on the body. So now we have carbon 6.985, hydrogen 10.248, and the nitrogen's obviously my smallest amount here. So when I divide them all by the 0.4111, I end up with an empirical formula of C17H25N. Number 28 wants to know which has the highest percentage by mass of nitrogen. And even though they don't suggest you do this without a calculator or just estimate it, this is one that you can easily estimate and save yourself some time, especially on a time test. So if you look at NH3 and use a periodic table, you quickly see it's about 14 out of 17 grams. Where CONH2, you find cobalt and see that it's 58.93 or about 59, plus the 2 nitrogen is going to be another 28 or 87, plus the 4 hydrogen is going to put it up around 91. So you've got about 28 out of 91 grams in that one. And then NH4, 2, SO4, again, because it's just 2 nitrogen with a lot of other stuff, it's unlikely it's going to have the most nitrogen, especially when NH3 is 14 over 17. But let's go ahead and take a look. I've got around 28 for the nitrogen. I've got about 8 for the hydrogen this time. Sulfur is 32, so 32 and 8 is 40, 68. And then the 4 oxygen is 48. So I'm way up over 100. I'm like 28 out of 150 something for this one. So clearly the NH3 is going to be the highest percentage. So number 29 tells you you have a compound M3N where M is an unknown metal. And so the formula is telling you you have 3 moles of metal to 1 mole of nitrogen. And then the other piece of information they give you is that you have 0.673 grams of nitrogen to 1 gram of the metal. So if I go ahead and change my 0.673 grams to moles, I know that 1 mole of nitrogen is 14.01. So the 0.673 divided by 14.01 equals 0.048 moles of nitrogen. Then since that's how many moles of nitrogen I have, I can multiply that by 3 because I know I have 3 moles of the metal. So that means I have 0.144 moles of the metal. But I also know that would be 1 gram of the metal. So 1 gram divided by 0.144 moles is going to give me my molar mass. So 1 divided by 0.144, I come up with a molar mass of 6.944 grams per mole. And if I look, it must be lithium. So it looks really complicated, but if you just slow down and take a look at it, you're being told the gram to gram ratio and the molar ratio, so you can use that to find your way to the molar mass of your unknown metal. Number 30 is another one that you could quickly do just using your periodic table but not actually calculating anything, because they want to know which one has the highest percentage of cadmium, and in each case it's 1 cadmium in the compound. So cadmium weighs 112.41, which really doesn't even matter here, but it's going to be 112.41 to 32, or 112.41 with selenium, which is 78.96, or cadmium 112.41 with tellurium, which is 127.6. So even though they said the percentage, remember, mass ratio is going to give you the same information. And we look at this, and you quickly see that CDS is going to give me the greatest percentage of cadmium.